All right, let's look at, we'll go to section 2. Now again, this first chapter, 4 sections, are mainly just getting us prepared for starting the actual calculus, which will be chapter 2. And a big thing is being able to look at, knowing about the different types of functions, that kind of thing. And in this book, like I said, the early transcendentals, these exponential, logarithmic, all the trig as well as inverse trig, all of that is introduced at the beginning. So that's kind of what we do a little bit in this chapter. Now, in this section, we start looking at functions. Okay, so pull that one up here. Section 2. All right. So what they do is they start talking about just different types of functions. Okay. Now, their domain and range, domains, that kind of thing. All right. So first one, polynomials. That's all. Every one of those over there is a polynomial. Okay. So as long as it's kind of in this form, okay, and all this is just you got x's, terms with x in them. Their exponents are numbers, not fractions. They're not negative. Just like these, you got x to the 4th, x squared, x to the 5th, x to the 3rd, x to the 1st. All of these are polynomials. Okay, so with polynomials, the domain is all real numbers. You can plug anything you want to in for x if it's polynomial. The degree of a polynomial is the highest exponent of x. All right, so over there, the first problem, the degree was 4. The second one, the degree was 5. The third one, the degree is 5. It has n real zeros or roots, values of x, at which p of x is equal to 0. Okay. All right. Polynomials. All right. Rational functions is just a polynomial divided by a polynomial. All right. So if I were to take one of these, forgot what it was, but anyway, so we got that over x minus 1. All right, you've got a polynomial divided by a polynomial. That's rational. Okay. What do you remember about rational graphs? That's important. Rational functions. Let's graph. I made that one up. Let's graph it. See, it may not give me anything good, but let's try it. All right. Let's say we graph it. That minus 2x squared minus 4 divided by, what is that? I put up on the bottom, x minus 1. All right, that's what I got. I could pick something better. What's going on with the graph here? What happens right here at 1? What happens if I plug 1 into that graph there? The bottom is 0, it's undefined. So for a rational function, I get a vertical asymptote with whatever makes the bottom 0. All right. So the big thing with those, and these will come up all throughout, everything we do in calculus, we'll have these rational functions. You have vertical asymptotes. You also will have a horizontal asymptote, possibly. And those are going to be really important as far as some of the calculus that we will do. So we want to remember that. All right. Let's see. Let's move on here. Okay, so we got polynomial, rational, and then they talk about algebraic functions. Polynomial and rational are algebraic. Also, any like the roots, square roots, any of that, those are also considered algebraic functions. Okay, so all of those fall as algebraic, and he's down here. They're going to give a little chart. All right, so they show that you've got one group of functions here called algebraic functions, and they do include polynomial and rationals. Okay, but also square root functions. Okay, and then you've got another group called the transcendental functions. Okay, now in that group you have, of course, your trig functions. We all know about trigonometry, right? We've all had that. And then exponential and logarithmic functions fall into that, as well as inverse trig functions and other types. So a transcendental function is really just a function that is not an algebraic function. Falls in that transcendental. Okay? All right, exponential, we're going to look at that when we get to the next section after this one today in more detail. All right, so I'm not even going to talk about that right now. All right, any questions or anything about that? Now, of course, a linear function is a line, right? Linear line. And they're usually in the form f of x equals mx plus b. You have a slope and a y-intercept. Okay, we're familiar with those. All right, also, something that we will see are going to be piecewise functions. Okay, so piecewise functions have definitions on different parts of their domain. Okay, now in order to be a function, every x must be paired with only one y. So that has to be true with the piecewise function as well. But so if I have, we do this when x is less than or equal to 2, and this when x is greater than or equal to 2. Well, that's going to, I'm going to have two y's there with one x. So that it doesn't work that way. So with the definition here, this would be when x is less than 2. This will be when it's equal to 2. That's when it's greater than 2. So every x is only represented once there. Okay. So this would be the graph of this piecewise function. Okay. So just notice, you really got three functions here. You've got g of x equals x, or y equals x, all right, which is just a line that goes through just like this, right? But you only graph it when x is less than 2. So everything from here over, I have graphed y equals x. That looks like that. Okay? G of x equals 3. All right, what would g of x equals 3 look like? Horizontal line crossing the y-axis at 3, right? We only do that, though, when x is equal to 2. So when we're here at 2, I've got a point right there, and that's all I've got. Okay? When x is bigger than 2, so from here over, I'm graphing the line negative 1/2 x plus 5. So this one would have a y-intercept here at 5. My slope is negative 1/2, down 1 over 2, down 1 over 2. But I only graph that line from 2 over. Okay. All right, so next, so those are piecewise functions. All right, we definitely see those some. Power functions. Okay, power functions are just if you've got x to some power. All right. Now, the way it works here, notice, if the power is even, so you got x squared, x to the 4th, x to the 6th, then this is what's going on. All right, so like x squared, and notice on this one, you've got, this is not the same as this as far as distance goes. These are going up 10, 20, 30, 40 like that, and this is not. All right, so just y equals x squared is just that regular parabola that goes up. Okay, if you have x to the 4th, it's still going to be that same shape, except when you get up to when you put a 2 in there, 2 to the 4th is going to be, 16? Whereas whenever I put 2 into this one, I just get 4. So it's going to start shooting up quicker than it will on the x squared one. If I have y equals x to the 6th, same thing. It's still going to be at 0, 0, and 1, 1, but then it's going to shoot up quicker. All right? But they're all that same bowl type shape. Okay? If it is an odd exponent, okay? So like x cubed, x to the 5th, x to the 7th, then x cubed, we go up like this, and then this side, which would be similar to this one, you know, that would be up that way if it was an even, because when you put a negative number in there and square it or fourth it or whatever, it's a positive. But since I'm having odd exponent, then if I put in -1, the cube of -1 is -1. So it's like this side over here is flipped and goes down. Okay, so I have this, and then if it's the 5th power, again, it's going to be stretched in a little more. 7th power stretched in a little more, for whatever power, however high you want it to go. Okay, and those are power functions. Any questions about that? Okay. Now the other one, that kind of leads to this other one, which is a root function. Okay. So with a root function, you got x to the 1/2 power. Of course, you remember, I think, x to the 1/2 is the same thing as square root x, right? Okay. X to the 3rd is the same thing as cube root x, so on and so forth. All right. So if that root is an even root, okay, then if x is below 0, it's a complex number, or not defined, right? Complex number. It's not real. So there's nothing from here over. But you go up like that. All right. If it's a 4th root, then you're still going to have 0, 0, and 1, 1. But when you get to 2 for a 4th root, you're going to have to be all the way over here at 8 in order to get to cube root of 8 is what will give you 2. So it's going to start stretching down more as you go. Okay. For an odd root, like a cube root, 5th root, you can take the cube root of a negative number. So you do have something over here, and it's just another tail that goes down like that. Right. If you go to the 5th root, it's going to be the same thing except stretch down a little more and a little more as you go along. Okay. Questions about that? Now, real quick, let me show you. So I think last week I gave you this 21 graphs to know. If you weren't here, this is in Moodle. All right, so notice what we've got here. And I think what we'll do is on Monday, we will go ahead and have our first quiz, but it'll just be over these graphs, okay? So no trig yet, till we won't get the trig stuff today. So, but just a little, just have 10 of these. All I'll do is I'll give you the picture. You need to write the equation of the graph. Okay, so if you see this one, the bowl, you're going to say y equals x squared. Okay, everybody follow that? So y equals x squared. There's x cubed. You just have the little tail that goes down like that. Okay. If it is absolute value of x, the shape is a V. All right. If it is square root x, that's the one we just looked at, then you've got that, right? If it is either a cube root or 1/3 power, you've got this along with one going that way. Okay. Remember the shapes. Okay, let's see what else we got here. Now this is a greatest integer function. Don't worry about it right now. Number 4, I'm not sure. It probably comes up in our book. I'm not sure. It did in the other one. But let's hold off on number 4. Don't worry about it yet. Okay. Now notice if you have y equals x to the 2/3 power, then what does that 2 do that's on, what's that 2? What does the 2 do that's on top there? So if I have x to the 2/3 power, what does the 2 do to the thing? Well, is it the same thing as that? Is that the same thing? All right, so I've got cube root of x squared. All right, so the top number is an exponent. Bottom number is the type of root that you've got. Okay, so if you think back at, if you go back to this 1/3 here, so if I have y equals x to the 1/3, I've got this, right? Well, if I square that, it's really not going to affect this side that much. Okay? But what does it do to this side over here? Well, over here, all of these are negative values, right? What happens if I square a negative? Positive, right? So this thing is going to flip up. So that makes that tail there go that way. So if it's 2/3, the graph will look like this. Okay, so any questions about that? All right, number 8, that is a rational function. Basic y equals 1/x. That will be, you have a vertical asymptote at 0 through here. You also have a horizontal asymptote at 0. So you have a little loop there, and you have a loop there. Okay? If it is y equals 1/x squared, then you have a loop here. And then what happens to this side over here when you square x? Then all these negatives, which were negative here, will become positive, and that flips this side up to where it looks like this. Okay. Now, remembering what all of these look like is going to be very helpful in doing the calculus stuff that we're doing. Okay. So all you need to do, and I don't even see your mouth. All I can look at is your eyes. You know, I can't tell. I can't tell if I'm looking at fear or what. You know, but all you got to do is just remember what these look like. Okay, and if you can kind of make sense, you know, of it, not just memorizing something, that's better. But remember what the shapes are. That's going to be very important later on. In a minute, we'll look at e to the x and ln of x. Okay. Don't worry about 10 right now either. That's just top of a circle. We'll look at those again. That'll come up another time. All right, transformations of functions and graphs. All right, did this in pre-calculus. Just remember, to move a graph up and down, you do what? You just add a number on the end, just like I did a while ago in Desmos to that graph. I added 1 and the thing moved up 1. So if you add a number on the end, that moves that graph up and down. Okay? How do I move the graph left and right? That's when you add a number or subtract a number directly to x. So if I add a number or subtract one directly to x, that is going to move that graph left or right. And that one actually moves it the opposite directions than what you probably would think. So if you add a number directly to x, which direction will that move it, left or right? Left. Okay, correct. If I subtract a number, moves it to the right. Okay. Now multiplying by numbers will either shrink or stretch or compress. Stretch or compress is the words he uses, vertically or horizontally. And let's don't worry about that too much right now. If this was pre-calculus, you could get into it a lot more, but let's don't worry over that too much now. All right, a few problems here. Okay, how do you obtain the graph of y equals 4 times x plus 3 squared plus 6 from the graph y equals x squared? Okay. Well, you've got three numbers in there that you don't have in y equals x squared. So we know y equals x squared, the shape of that is a parabola, right? What does the plus 6 do to the graph? How does that shift it? Up 6 units, right? What would the plus 3, which direction would that shift it? Left 3, all right? The 4 would scale the graph vertically, okay? So she's going to stretch it a bit, all right? So for that one, we could say, I'm not going to write it down, but it shifts the graph 3 units to the left, scales the graph vertically by a factor of 4, and then shifts the graph vertically by 6 units. That's what we said, okay? Any questions about that? All right. The graphs of the functions f and g in the figure are obtained by vertical and horizontal shifts and scaling of y equals absolute value x. Find formulas for f and g. Okay? So it looks like these are rigid shifts because we're just going, we go here to here, same thing here. So it looks like it hasn't been stretched any. All right, so to write a graph for f of x there, how have we shifted this basic y equals absolute value x graph? We went up how many? 3, and then to the right 2. All right. So the up 3, let's do to the right, what did it say, 2? How would I write that? I do that directly to x. If it moves to the right, then that would be minus 2. So x minus 2. And then up 3 would be plus 3. All right, that would be my f of x. Okay. Now g of x, the vertex of this thing is here, right? So it is moved to the right 2. So that would be directly to x plus 2. It is moved down 1, so I would subtract 1. But it's also opening downward. What do I do to make it open downward in the equation? Negative. All right. So does the negative go with the x, or does it go in front? In the front. If it's reflected across the x-axis, the negative goes in front. So that would be g of x equals negative x plus 2 minus 1. Okay. Any questions about that? It says sales record indicate that if Blu-ray players are priced at $250, then a large store sells an average of 12 units per day. If they are priced at $200, then the store sells an average of 15 units per day. Find and graph the linear demand function for Blu-ray sales. For what prices is the demand function defined? Okay, so the word in there is linear, which means what? Line, right? So demand function, I need to know what x and what y is. Okay, so would I need to have the price be x and the units per day be y, or do I need the units per day be x and the price y for a demand function? What does demand refer to? Does it refer to the price or how many units you sell? How many units that you sell, right? So the demand function, that means the y needs to be how many units you sell. Does that make sense? Okay. So I have 2 points there. So I would have $250 when it's $250 they sell 12 units. When it's $200 they sell 15 units. Got 2 points. Okay. All we're doing is just reviewing a little bit with lines, all right, because you got to be able to get the equation of a line in calculus. So to find the equation of the line that going through these 2 points, you got to have your slope first. So remember, the slope of the line is the difference in the y's divided by the difference of the x's. So and it doesn't matter which point you start with. I want to say 12 minus 15 over 250 minus 200. Okay. That will give me negative 3 over 50. Okay. That was my slope of my demand function line. Okay. Now, we need to remember point slope form. All right, that is point slope form. One of the big things, of course, that we do in calculus is derivatives. And one big question with derivatives is, what is the equation of the tangent line, at a certain point. So we have to do a line. So when we do that, point slope form. Now you can do it. You can do it the other way if you want to, but I always use point slope form. All right. So let's plug x and y in. You can pick either point you want to. It doesn't matter. You'll end up with the same answer. I used that top one there. So I did y minus 12 equals negative 3 over 50 x minus 250. Okay. Now do a little algebra, a little ninth grade algebra. All right. So multiply and add 12. That will reduce to be y equals negative 3/50 x plus 27. Okay. So as far as the function goes, I can say the demand is equal to negative 3 over 50 times the price plus 27. So that would be my demand function. For what prices is the demand function defined? All right, let's say that we graph this on Desmos here. Use x. All right, this is what we've got, okay? So, what is this graph here? What is this axis, I mean? The x-axis, what is it? Which one is it? P, which is what? Price, okay? So, price, and then this away would be the demand, the amount, all right? So, the question is, for what prices is the demand function defined? Well, what happens when we keep going this away? What happens over here? Are you going to start giving things away? You're going to start giving the Blu-ray players out, so you can charge more money? That doesn't make any sense, right? So the highest amount that you can get that applies to this will be $450. Because when you go above $450, you will actually have to give away the Blu-ray players. Okay, so that doesn't make sense. All right, so you would just say 0 to $450. Okay. All right, any questions about that? Now we're off track a little bit with our schedule. Okay, so we'll just kind of adjust it as we need to. This is our first time through this book, so a lot of this stuff at the beginning is important. We will adjust things as we need to. But all right, this next one says write a definition of the function whose graph is given. All right, so here is a piecewise function, and we want to write that definition of that function. Okay, so g of x equals. Okay, so notice where x is defined, okay? So that first part there at the top, x is going everything from negative infinity up to 3 will be this one. Everything from 3 to positive infinity will be that one. So I will say if the top will be if x is less than 3. The bottom one would be if f is greater than or equal to 3, because that's where I have my dot, right? That's where it's a solid dot. All right, now these are lines, okay? So remember with lines, slope and y-intercept, okay? What is the y-intercept of this one? 1. All right, you may not be able to see it. Okay, 1. And then what is my slope? It's like up 1 over 1, up 1 over 1, up 1 over 1. So x plus 1 would be that line, okay? So I'm going to write g of x equals x plus 1 if x is less than 3. All right, now for this one, you could either take 2 points and find the equation that way. I think what I would notice here, though, is the slope is down 1 over 3. So I could go here and go up 1 and back 3. And that tells me that my y-intercept is actually at 3 there. And then my slope is down 1 over 3. So negative 1/3 x plus 3 would be my equation there. Okay, there you go. All right, graph the following functions. All right, that first one looks rough. Oh, it's not though. Okay, good. All right. All right, so let's just take each of these and we'll graph them. All right, these are piecewise functions. All right, so first we got f of x equals x squared minus x over x minus 1 if x does not equal 1. And we've got 2 if x equals 1. Okay? Now when I first looked at that, I thought, well, that's bad. That's a rational function. We've got to do a lot of stuff to that. But what do you notice about x squared minus x over x minus 1? Can you reduce it? You can factor an x out of the top. So if you've got you can factor an x out of the top, you get that, and then the x minus 1's cancel, I get x, right? So that is really just the line y equals x, except whenever x is 1, you would have a hole in the graph right there, because it's not defined, because you'd be dividing by 0, okay? But that's fine, because here, we do this one everywhere except when x is 1. And then when x is 1, we do 2. So this graph would be, all right, so I would just graph that line there. All right, except at when x is 1, which would be right there. So that would be the top one, okay? And then the bottom one would be, I need to graph 2 right there. That would be the graph of that piecewise function. Any questions about that? All right, so we graph this one everywhere that x is less than negative 1. Okay, so negative 1 is here. All right, so if I graph this function, okay, what you might want to do is say, well, what is my point when x is negative 1? Well, if I plug negative 1 in there, negative 2 times negative 1 is 2 minus 1 is 1. So negative 1, 1 will be an endpoint there, and it will be an open circle. Okay, so I just plugged in that negative 1 where it's changing graphs at. I got this point, so that's where this one will start. And I'll just look at the slope. The slope is negative 2, so negative 2 over 1, so that would be down 2 and to the right 1. But I need to go in the opposite direction. So rather than going down 2 to the right 1, let's go up 2 and back 1. Okay, same thing. So up 2, back 1 would give me a point right there. That would be that part there. Okay. Now from negative 1 to 1, including those two, I'm just graphing f of x equals 1. All right, well, what does y equals 1 look like? Horizontal line. Okay, horizontal line. So at 1. So from here to here, I'm just going to go across. And that is going to include that point now. Okay. And now this one, 2x minus 1. All right. If I put 1 in the place of x there, I get 2 minus 1 is 1. I get 1, 1, which is the point right there. So this is all just connected. Okay. Slope is 2. Up 2 over 1 would be right here. That would be that part. That would be the graph of that piecewise function. Now that's all that's left. All right, shifting these graphs around a bit. Okay. All right, so for these four here, excuse me, it says use shifts and scaling to transform the graph of f of x equals root x into the graph of g. Okay, so a couple of them has used function notation, and then a couple of them you just got the square root in there. Okay, so the first one there, g of x equals f of x plus 4. Okay, so if I add 4 directly to x, what does that do to the graph? Which way is it shifted? Left 4 units. Okay, so that one. And it's a rigid shift, so I would have a point there. I have a point right here. Normally with the square root function, I go over 4 and up 2. So I would go over 4 up 2 right there. That would be the equation, okay, the graph. All right, the next one, g of x equals 2 times f of 2x minus 1. Okay. So that one's a little bit more complicated. Okay, this one, what I would do on this one, I think, is take the points that I know that's on the regular square root function. So if I have y equals root x, I have 0, 0, 1, 1, 4, 2. Got that, okay? So I'm going to take these 3 points, 0, 0, 1, 1, and 4, 2, and I wanted to transpose those into the correct point that those will change to from all that, okay? Now, first thing I will need to do on this is rewrite it like this. Need to factor that 2 out of 2x minus 1 because I got to have that however it's going left or right, it has to be directly to x there. Okay. All right, so what does this 2 here affect? Will that affect x or will that affect y? I'm saying 2 times f. What is f of x the same thing as? Y. So this 2 here is being multiplied directly to the y. So I can go through here and I can say, okay, the y, and that's all. There's nothing on the end. If I had a number over here in the end I was adding or subtracting, that would affect the y. Okay? I don't. So 0 times 2 is 0. 1 times 2 is 2. 2 times 2 is 4. Okay? Now, the x's. I got 2 things. I've got 2 and I've got a minus 1/2. Okay? And the best thing to do with the x's is to just set those equal. So I would say 2, and I probably could leave it 2x minus 1. I tell you what, let's just ignore that. If you were going to, if you didn't have these 2's here, you could move it easier. So let's just leave that part off there. All right. Let's just say 2x minus 1 is equal to 0. If I solve that, that means my x there will change. I'll add 1 divided by 2 will be 1/2. So that now will become 1/2 0. Okay. Same thing here. When x is 1, I will add 1 is 2, divided by 2 is 1, x will become 1. And then for 4, add 1 is 5. Divided by 2, 5 over 2 is 2 1/2. Okay? So what do I have? I have these points. So I'll have 1/2 0. So you got to go up to. All right, so 1/2 0 is right there. 1, 2 is here. 2 1/2, 4 is here. That would be how that would affect that graph. Okay. Not going to do this one. That one's pretty easy. Square root of x minus 1. How would that one shift? Minus 1 would go to the right 1 unit. Correct. All right. This one, the minus 1 would move it to the right 1. The minus 5 would be down 5. The 3, you would have to multiply your y's by 3. All right. Those, I guess we'll do those real quick. All right. Look at g of x equals negative 3x squared. Okay. So if you take that parent function that we've got, y equals x squared. All right. Remember, then you have a vertex at 0, 0. You've got a point at 1, 1, negative 1, 1, 2, 4, negative 2, 4. Okay. So I have these points. All right. So what I would do here, I would say, all right, I've got negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. All right. So the x or the y's are going to be affected by that negative 3? Which one is going to be affected by the negative 3? So how do you tell? All right. Well, the function is x squared, right? It's negative 3 times the function. All right, so the function is y. All right. Now, if you had something going on to x inside the parentheses, inside that square, that's when it affects x. Right? That's just going to affect y there. So you can just take each of these points, Your x is going to stay the same. Your y would be negative 12. Zero is going to stay the same, right? Because 0 times negative 3 is same. 1 times negative 3 is negative 3. 4 times negative 3 is negative 12. That will be your points, all right? So to graph that, then we would have got to go down to 12. Zero, 0, 1, negative 3, 12, 12. All right, that would be your graph. Okay, so it shifted down, brought in by a factor of 3. All right, so the direction said use shifts and scalings to graph. Okay, now quadratic function, right? And you pre-cal, you would have, probably could have found the vertex and did all of that. We want to use scalings in shifting. Okay, so since we're pushed for time, what you could do, all right, is you could rewrite this where it's in more of a vertex type form, or a form where we can do the shifting, right? So what you could do is group the x squared plus 3x together like that, okay? Now, if I can make this a perfect square, then I can factor it. It'll look really nice where I can shift it. All right. So how do I make this a perfect square? How do I determine the number to put here to make it a perfect square? Take 3. What do we do to it? I know some of you know because I taught you in pre-cal. Take the 3, half it and square it. Remember that? Half it, square it. That gives you the number right here that makes this a perfect square. All right. Now it's kind of weird since you got a 3, but we can deal with it. All right. So half of 3 is 3 over 2. What is 3 over 2 squared? 9 over 4. All right. If I add a 9 over 4 right there, that is now a perfect square. Okay. I can't just randomly add a 9/4 there. So I need to subtract that back off of the end. So I'm going to say minus 9/4 there. Okay. Now this is a perfect square. It will factor to be x plus, and if it's a perfect square, this number is always half of that middle one. So half of 3 is 3/2. And then negative 5 minus 9/4 is negative 7 1/4. Okay. Now with that, you can graph that with by shifting. Okay. The minus 7/4 would move that parent function down 7 1/4. The plus 3/2 would move it to the left 1 1/2 units. Okay. So I could say 7 to the left 1 1/2. That'd be about right here. And then the rest of it doesn't matter. Just go up. All right, that'd be the graph. Okay. Questions about that? All right. You know what's the shape of it going to be anyway? If it's absolute value. It's going to be a V. All right, you know that. Okay. We know the plus 1 on the end will shift it up 1 unit. Okay. I don't know about 3x minus 6. I don't know. All right, but we can work with this a bit. So let's take the 3x minus 6. Let's factor out a 3. if I've got 3 times x minus 2 in the absolute value, then the absolute value of 3 times the absolute value of x minus 2 is the same thing. So I can rewrite that as 3 times absolute value x minus 2 plus 1. Okay. All right, so the 3 and the 1 is going to now affect the y value, and then the x minus 2 is going to actually affect the x. Okay, so what I would want to do here then that would be my points, right, for my normal absolute value function. That's it, right? So the x minus 2, if I set x minus 2 equal to 2 there, then I just add 2. So that would change my x to a 4. Right, and what am I doing? This minus 2 is really shifting it to the right 2 units. So that's just adding 2 to each of those x's. All right, so that would be 3, 2, 1, 0. Okay. Now the other one, the y's, I need to multiply by 3, and I need to add 1. So for my y values here, you multiply before you add. Okay, that's the order of operations, follow order of operations. So I would say 3 times 2 plus 1. So that would be 6 plus 1. That would change to 7. Okay. 1, I would say 3 times 1 plus 1. That would be 4. 0 times 1 plus 1 is 1. 1 times 1, I messed that up. 3 times 0 plus 1. 3 times 1 plus 1. Or that'd be back to 4. And then the same thing there. 3 times 2 plus 1, that would bring us back to 7. Okay. So that would be my points. All right, so I would have, for my graph, got to go up to, let's see, 1, 2, 3, 4, and up to 7. One, 4, 2, 1. That would be the graph. All right. Functions, shifting functions. Okay. Any questions about that? That is section 2. Okay. All right. So next time we will definitely look at get 1.3 and try to get 1.4 knocked out too next time. And after that, we'll get into chapter 2, actually get into calculus. We're still kind of warming up for the calculus part. So be sure to get in my math lab. I'll talk about that again. Be sure to get in my math lab, okay? If you haven't already, work on 1.1, 1.2 homework, okay? On the 21 graphs to know, all right? Remember to know all the graphs. Just worry about numbers. I won't get too close. 1 through 9, but not 4. Okay, 1 through 9, but not 4. Then it's saying 10 questions. I guess you won't have 10 questions. Okay, you want to have some more on there, or does it matter? You don't need more. Okay, all right. So just know those. Okay, so be able to identify those, and we'll have our first little quiz then. So. All right. If you need anything, let me know. Send me a message, and I'll be happy to try to help you. So I will see you next time.